Hello wonderful person, this is Anton, and today we're going to be discussing supernova. And actually this one really interesting paper that claims to have officially, for the first time in history, seen a supernova explode in real time, with the scientists even observing the star approximately 130 days before the supernova occurred as well. In other words, unlike previous observations where we only get to see the final result of the supernova, or the supernova remnant that you see right here, or some other observations where we only get to see the explosion or the flash, in this particular case, for the first time ever, the scientists have observed the star for over a year, actually seeing what happens during the entire process. And more importantly, they actually observed a star that we usually refer to as a red supergiant. So basically, a star that's very similar to Betelgeuse. Betelgeuse that a few years ago was all over the news, because scientists thought that maybe it's going to go supernova as well. And though today we know that all of this statement was probably because of some kind of a cloud in front of Betelgeuse, trying to figure out what signals we should be looking out for and trying to actually predict how these stars usually act before going supernova is of course kind of important in order to detect any other potential supernova both in the vicinity of planet Earth and somewhere farther away in order to learn more about them scientifically. But before we start, let's clarify a few things. First of all, when it comes to supernova, there are obviously different types of these explosions all over the universe. But the majority of the supernova we observe in the night skies can be generally defined as one of two types, either type 1 supernova or type 2. Type 1 supernova doesn't actually have any hydrogen on the inside. And that's because normally this is when white dwarfs explode, they don't usually possess hydrogen. Whereas type 2 supernova will always have hydrogen somewhere in them. And that's because that's when some other stars, usually larger and more massive stars that are not white dwarfs, explode, releasing large amounts of hydrogen and other elements all over the universe. And of all different candidates in the vicinity of planet Earth, it's really stars like Betelgeuse that are red giants that are of particular interest to us, simply because they are most likely to be the next on the list to go supernova. And these will create type 2 supernova, eventually producing some sort of a neutron star on the inside. But the thing is, stars like Betelgeuse, the red giant stars, are normally anywhere from about 8 to maybe 15 masses of the Sun, and so when they do explode, they don't actually produce the most powerful supernova, and generally are not expected to be super active before that as well. As a matter of fact, their supernova are usually referred to as faint type, mostly because they're somewhat difficult to see, especially from farther away distances. And pretty much most of the modern theories predict that stars like Betelgeuse right here are actually going to sort of remain more or less the same up until the last point before they explode. So in other words, their actual supernova could be completely surprising and would come out of nowhere. Or at least that's the theory. The recent paper that we're discussing today presents completely different evidence and suggests that this is not really correct. But before that, let's kind of go through the lifetime of a typical red giant. So this is something that's obviously more massive than the Sun by at least 8 to 10 times. And here, for the first 10 million years or so, most of these stars will be basically burning hydrogen, producing helium. So exactly what our Sun is doing right now. And during this time, this is when these stars are known as red supergiants. They're extremely low in density, they're also extremely large in volume, and will often stretch to really far away distances. As a matter of fact, the majority of these stars expand way past the orbit of Mars, and in this case, this particular star was approximately 1100 times the radius of our own Sun. So these stars are huge, but not really super dense. As a matter of fact, their density is extremely low. But then after about 10 million years, for the most part, the hydrogen will be almost gone. However, now there's quite a lot of helium, and this is of course the next step. Now helium starts fusing as well and starts burning, producing even more energy and even more heat. Something that usually happens for approximately a million years or so, and will normally also dramatically increase the temperature of the star, but also shrink the star, increasing its total density. So a lot of these red giants become slightly smaller, but way hotter and start producing even more energy. At least for approximately a million years or so. All of this helium burning on the inside ends up producing quite a lot of carbon and quite a lot of oxygen. But obviously at some point this also runs out. The next on the list is carbon. Carbon starts fusing once helium is gone and once enough carbon is present to essentially initiate the reaction. This increases the temperature and the density even more and is an extremely violent reaction that usually only lasts approximately 1,000 or so years. And this also ends up producing heavier elements, for example things like aluminium, things like magnesium, but also things like neon. And neon is where things get really interesting. Mostly because, well, first of all, the star becomes even hotter and becomes even more dense, but also because the actual burning process in a typical red giant will only take approximately 3 years, something that's measurable in a human lifetime. And neon burning also produces oxygen, which then starts burning as well. And so once there's no more neon left, oxygen is next. Although naturally that's not really the same kind of oxygen burning that we have on planet Earth. Here we're talking about the fusion of the actual atoms, which then start to produce other stuff. In this case, they produce a lot of different things, including things like silicon. And oxygen burning is also an extremely furious process that usually only lasts only a few months, something that's technically measurable once again in a human lifetime. And then at the end, for just under 1 week or possibly a few days, a lot of these stars will also start burning silicon, which will then fuse into nickel, and this nickel will then slowly decay into the stable version of iron, which unfortunately upon fusion doesn't actually produce any more energy and instead actually takes away energy. Although even this particular process actually has several different steps. And once the star starts producing nickel and iron, that's when everything ends. Since there's no more energy produced to prevent the star from collapsing, it reaches a point where it's no longer able to support itself, undergoing what's known as the core collapse, and this produces the supernova that we refer to as the Type II supernova, with pretty much everything summarized in this image right here. But the thing is, that's basically the theory and, to some extent, a simplified theory of what we believe happens inside these stars. And the observations from the recent study suggest that things do not always go as planned. So first of all of this comes from the survey that you see right here, known as the Young Supernova Experiment. And back in the summer of 2020, the scientists using Pan-STARRS telescope detected some really unusual emissions, very explosive emissions, coming from an extremely distant star in a galaxy approximately 120 million light years away from us. The galaxy known as NGC 5731, that sort of looks like this if you were to look at it from planet Earth. As you can see, it does actually look pretty far away. But despite the distances, whatever was happening with the star was extremely explosive and was visible by various telescopes. But it was not a supernova, and so the scientists became really intrigued and started to observe the star, collecting constant data from this particular region. To their surprise, a few months later, in September of 2020, the star clearly went supernova, displaying all of the stereotypical signs of a Type II supernova from a red giant very similar to Betelgeuse, approximately 10 to maybe 12 masses of the Sun in mass. The supernova was officially named SN 2020 TLF. And so that was basically the beginning of the story here. For the next 300 days, the scientists decided to observe and see what actually happens to the star as the supernova progresses, essentially resulting in the longest and the most detailed observations of a pre-supernova and post-supernova activity, basically tracking everything in real time. And I know that someone in the comments is going to say, wait, that can't be in real time, it happened 120 million years ago. Well, that's not entirely true, mostly because our friend Albert Einstein would disagree. It didn't happen 120 million years ago, because everything in the universe is relative and there is no objective time or objective space. And that's of course the idea behind the theory of relativity. But that's another topic for another day. For now, back to the supernova that was observed in real time. And so the most unexpected discovery in this particular case was actually that observation from summer of 2020 of the pre-supernova activity that has never been seen before in red giants, suggesting of course that certain red giants seem to not actually go supernova quietly. They do experience very violent events prior to the actual explosion at the end. But the end result is still the same, a cloud of gas around the star and a neutron star in the center. And these unusual emissions prior to the actual supernova suggested that something must have happened inside the star, very likely during those last few stages of actual nuclear processes, so either involving oxygen, neon, or possibly even silicon. Moreover, further observations suggested that there was quite a lot of gas present around the star right before it went supernova, very likely produced by those violent eruptions in the summer of 2020. And interestingly here, the scientists were even able to calculate the total mass of the gas released every year and even how big the gas was despite the distances involved. In this case, they suggest that the gas itself was approximately 6 astronomical units away from the star and was most likely released at approximately 1% of the mass of the Sun per year, with all of this gas then violently pushed away from the star when the final supernova occurred. But the question here was, well, what exactly happened in the summer though? What caused these unusual explosions prior to the supernova? Well, here the scientists believe that it was either something related with the gravity waves emitted during the neon or oxygen burning in the last few months of the star's existence, or possibly related to the actual silicon suddenly exploding and producing a lot of energy, something that we sometimes refer to as the silicon flash. And by detecting these particular signals from this star, the scientists can now start looking for similar signals from other galaxies and possibly find more similar stars going through similar reactions. And this one day might help us understand what's going to happen to Betelgeuse, what's going to happen to Antares, or a lot of other similar stars very close to us that at some point going to explode as well for very similar reasons and probably with very similar effects. But unfortunately for now, that's kind of all we know. Once the scientists find more similar stars or discover something else about this particular supernova, I'll make sure to follow this up with another video. Until then, check out all of the links in the description below, subscribe, maybe share this with someone who loves learning about space and sciences, and maybe come back tomorrow to learn something else. Maybe support this channel on Patreon by joining channel membership or by buying the Wonderful Person t-shirt you can find in the description. Stay wonderful, I'll see you tomorrow, and as always, bye bye.